From her computer in Laurel, Maryland, Christina Beck studies the history of Mars. Christina, a planetary geologist, uses data from the APL-built and operated CRISM instrument on the Mars Reconnaissance Orbiter to analyze geologic features on the red planet.
Exploring the geology of Mars is similar to the way that we look at the rock record on Earth. One way we do this is by analyzing stratigraphy, or studying the layers of the ancient rocks that record changes through time. The Grand Canyon, for example, exposes over 1 billion years of the Earth's history. And this history is recorded in the layers of rocks, which tell geologists about the ancient environments that once existed on Earth.
Valle Marineris is considered the Grand Canyon of Mars and is a planetary geologist's playground.
If we take Valle Marineris and project it onto the Earth's globe, it would actually stretch across the entire continental United States. It's about 4 miles deep, and because of this exposes some of the most ancient crust on Mars.
How Valle Marineris was formed remains a point of debate among scientists, but would provide important insight into the history of Mars.
Valle Marineris appears to have formed as a result of the enormous amount of stress that the Tharsis Bulge, or the largest set of volcanoes in the solar system, have placed on the crust. And this massive load causes stresses that basically rip apart the crust. Recently, however, it's been hypothesized that while it was rifting open, it also experienced strike-slip faulting, like we see in California with the San Andreas Fault.
Christina analyzes geologic features on Mars using CRISM data to study their mineral compositions.
If Valle Marineris simply pulled apart, we would expect that the geology on the north side and the south side of the canyon walls to match up with each other. If significant strike-slip faulting occurred, then those rocks would be offset from one another, and the north side and the south side wouldn't match up. So we target the CRISM instrument to observe the walls of Valle Marineris and to look at the different primary and secondary minerals that are exposed. The secondary minerals, or alteration minerals, show us how that primary material altered or weathered in the presence of water on ancient Mars. And we can find these signatures of primary and secondary minerals in the CRISM spectral images by looking for key absorptions at the infrared wavelengths that CRISM detects, and that help us to identify the minerals that make up the rocks. Using the CRISM data, we can put together a very simplistic geologic profile of the rock record exposed in Valle Marineris, like the geologic profile of the Grand Canyon. Most of the canyon walls shows that the secondary minerals formed in the presence of water only at lower temperatures. However, using CRISM, we found a very localized region to the west, where we see magma dikes that cut through the crust, and we see secondary minerals that must have formed at higher temperatures. And these higher temperature minerals are exposed on both the north side and the south side of the canyon walls.
So what do these secondary minerals and their location tell us about the Grand Canyon of Mars?
Well, the CRISM data tells us something about the formation of Valle Marineris. And because we see these special high-temperature minerals directly across from each other on the north and the south side walls, we know that the formation of Valle Marineris is inconsistent then with strike-slip faulting. So by mapping out these minerals with CRISM, we see that Valle Marineris formed dominantly through extension or rifting of the Martian crust.